In problem number 6, we have a test plane flying in a straight line with positive velocity v of t in miles per minute at time t minutes, where v is a differentiable function of t, and selected values of v of t for t between 0 and 40 inclusive are shown in the table above. In part A, we want to use a midpoint Riemann sum with 4 subintervals of equal length and values from the table to approximate the integral from 0 to 40 of v of t dt. Show the computation that leads to your answer, and using correct units, explain the meaning of integral from 0 to 40 v of t dt in terms of the plane's flight. Well, if we want to have 4 subintervals, our original width is 0 to 40, we divide 0 to 40 by 4 and we get 10. And so that means that the left end point of the first rectangle will be 0, the right will be 10, then 10 to 20, 20 to 30, and 30 to 40. And the midpoints of each of those will give us the heights. So the base of each of the rectangles is 10, and the heights of those rectangles will be 9.2 will be at 5, which is 9.2, at 15, which is 7.0, at 25, which is 2.4, and at 35. So for A then, we simply have 10 times 9.2, and each one of them will be multiplied by 10, so I'll factor that out. So we have the integral from 0 to 40 of v of t dt, and since we're approximating, that's roughly equal to 10 times 9.2 plus 7.0 plus 2.4 plus 4.3, or 10 times 22.9, which is 229. Miles would be the units, and that would be the distance flown by the plane for t greater than 0 but less than 40. In part B, based on the values in the table, what is the smallest number of instances at which the acceleration of the plane could equal 0 on the open interval from 0 to 40? Justify your answer. Well, acceleration is the derivative of velocity, and so we want to find out what's the smallest number of instances at which the derivative of that function will be 0. You have to think back to what it is that guarantees us a 0 derivative, and that would be Rolle's theorem. Rolle's theorem will guarantee the existence of acceleration equaling 0 when we have a continuous function on a closed interval that is differentiable on an open interval. And since we're told that this function v is differentiable, then it's both continuous and differentiable. Now the only other criteria is that we need to start and end at the same endpoint, at the same y value. So all we have to do is find out, since we know it's continuous and it's differentiable, we need to find two y values that are the same. And so that happens at t equals 0 and t equals 15. Since the function is continuous and differentiable and v of 0 is equal to v of 15 and both are 7, then there must be some point in that interval where the acceleration is 0. So that's one point that has to be 0, where the acceleration has to be 0. Next, we have the interval between 25 and 30, which both have velocities at 2.4, and since the function is continuous and differentiable on that interval, there also must be some point between 25 and 30 where the acceleration is 0. And so v of t is continuous and differentiable on 0 to 40, and v of 25 equals v of 30 equals 2.4. Then a of t has to equal 0 at least twice. And it may be more than that, but it can't be less than that by Rolle's theorem. Okay, part C says the function f defined by f of t is 6 plus cosine of t over 10 plus 3 sine 7t over 40 is used to model the velocity of the airplane in miles per minute for 0 to 40. According to this model, what is the acceleration of the plane at t equals 23? So we're going to go to the graphing calculator, we'll enter that function, and so we have that there, and what we'll need to do is find the derivative of that function at time t equals 23. So we go back to the home menu, math, scroll up to nderiv, vars, y vars, function, y1, comma, x, comma, 23, and we get negative 0.408, and that would be in miles per minute squared. We'll continue with the next part in the next video.